Hey guys, and welcome to today's video, which is going to be about the chain rule for derivatives. So why do we use the chain rule? Well, the main reason that we use the chain rule is to deal with taking the derivative of composite functions. And just as a reminder, if you've forgotten what a composite function is, it's when you take a function of a function. So it has the notation g of f of x, or g and then this little O looking thing of f. So for example, if f is x cubed and g of x is x squared plus x, then g of f of x is going to equal to x cubed squared plus x cubed. And then you can go and simplify that. So we're just putting in f into g. Now let's actually get into the nitty-gritty of things and how do we actually get the derivative of a composite function. So when we're taking the derivative of a composite function, what we want to end up with is this right here. We want to end up with this expression. And knowing your algebra, which might seem a bit unexpected in this case, but think about how you can get to this point while taking the derivative of something that is far easier and straightforward. So I hope you had a go at it, and let me show you this very simple realization that you can make, which makes the chain rule make perfect sense. So we can rewrite this as the derivative of our composite function, but now instead of taking it in respect to x, we're going to take the derivative with respect to f of x. And if you can see where I'm going, now maybe you should try yourself again. And then we're going to multiply this by the derivative of f of x in respect to x. And would you look at that? This cancels out, and what are you left with? You're left with the derivative of the composite function in respect to x. So this is actually very simple if you look at it. The main difficult part is coming to realization. And when you look at this makes perfect sense. So I hope you can now apply this in the next few examples. So our first example is we want to take the derivative of g of x, which is sine of x squared. And what you have to do is realize that the x squared is your f of x, and the sine of x is your g of x. So what do we do? Well, in order to get the derivative of sine of x squared in respect to x, this will be the same thing as taking the derivative of sine of x squared in respect to x squared, and then multiplying this by the derivative of x squared with respect to x. Because these two will cancel out and you'll be left with what you want, which is this composite function right here. So let's go ahead and do that. So in this case, we're just going to assume that x squared is x, because that's exactly how we're treating it. This variable, don't think of it as x squared, just leave it as x in your mind. So knowing what we know about derivative rules, we can say that this equals to cosine of x squared. But now, we couldn't just leave it at that. We have to multiply it by the derivative of x squared with respect to x, which is 2x. So your derivative is going to end up being cosine of x squared times 2x. Let's look at a second example. In this case, g of x is the natural log of 3x to the power of 5 plus 9. So in this case, you have to recognize that the 3x to the power of 5 over f of x, and that the natural log of x is our g of x. So, like we did previously, in order to get the derivative of the natural log of 3 times x to the power of 5 plus 9 with respect to x, we have to take the derivative of the composite function with respect to f of x. which in this case, 3x to the power of 5 plus 9. And then we multiply this by the derivative of 3 times x to the power of 5 plus 9 with respect to x. And once again, you can see that these two terms cancel out and you're left with what you want, the derivative of the composite function with respect to x. This is very simple. This is a very simple way to cancel terms out in fractions. You've been doing this your entire life. You know that if 3 over 4 times 4 over 2, this is going to cancel out and you're going to have 3 over 2. This is exactly the same logic. And it might seem a bit unintuitive to apply this where you're applying it kind of to a notation, right? dy dx. Most of the time you view this as notation and never, almost never do you view this as a fraction. But in this case, it's very useful to open your eyes and realize that this is also a fraction. So the derivative of the natural log is 1 over x, but in this case, our x is 3x to the power of 5 plus 9. So we're going to have 1 over 3 times x to the power of 5 plus 9 times the derivative of that, which is going to be 15x to the power of 4 plus 0. So our end answer is going to be 15 times x to the power of 4 over 3 times x to the power of 5 plus 9. And then you can simplify this by dividing every single term by 3. So you're going to end up with 5 times x to the power of 4 over x to the power of 5 plus 3. And that's going to be your derivative. This is the derivative of our composite function right here. Okay, let's move on to our next example with e to the power of x. So in this case, our g of x is going to be e to the power of sine of x. Now, in order to get the derivative of e to the power of sine of x with respect to x, just like we did before, we recognize that sine of x is our f of x, and e is our g of x. We're taking g of f of x. That's our composite function. So, in order to take the derivative, we're going to take the derivative of e to the power of sine of x over, or with respect to sine of x times the derivative of sine of x with respect to x. Once again, you can see these two terms cancel out and you're left with the composite function with respect to x, the derivative of the composite function with respect to x. And we know that the derivative of e to x to the power of x is just going to be e to the power of x, and in this case our x is sine of x. So we're going to have e to the power of sine of x, but now we have to multiply it by the derivative of sine of x, which is cosine of x. And once again, there we have it. So I actually very like the chain rule. In my opinion, it's very important to understand because then you really understand derivatives once you realize that you can work with them as fractions because that is what they are. It's a very small change in y over a small change in x. That's your slope. And if you can express your slope as a fraction, you can definitely express your derivative as a fraction because your derivative is your slope when it's infinitely small. So this concept, I really hope you get familiar with it, of looking and viewing derivatives in this type of manner, because later on in calculus, you will definitely come across this way of looking at the derivatives and their notation. So I hope you enjoyed.